Alright, now we're going to talk about error. And there's two different kinds of error. There's systematic error, or determinant error, and then there's also random or indeterminate error. So systematic error is where you have reproducible errors. There's some flaw in calibration, in the instrument, in the procedure that affect all of your measurements in a predictable or similar way, in the same way. So, for instance, if the data in pink are the true data, then you might have something that shifts all of that up, or all of that down, or it changes the slope of all of those that line of best fit, so it changes the position of the measurements. So things that can affect that are something like interference, poor calibration, issues with instruments, bad experimental design, stuff like that. And systematic errors are something that you really, that all researchers are always sort of on the alert for. And so there's lots of different ways that you can look for them. But it's really important, because when you're discovering new data, or when you're taking new measurements and trying to discover new knowledge, you want to make sure that your data is actually accurate, and both accurate and precise enough to be able to draw conclusions from, and to make new discoveries. So this is something that all researchers are very interested in and definitely alert for at all times. So there's lots of different things you can do. You can analyze reference materials or lab fortified blanks. So what a lab fortified blank is when you have a sample, you know a lot about it, you make a sample in your lab that has their similar composition, similar matrix, and then you analyze that, but you already know exactly what's in it. So if you get the same, if your measurements say the same thing as what you put into the sample, then you know that your that you don't have systematic errors. You can also analyze blanks. If your blank isn't zero or isn't what you expect it to be, you know there's a problem with the instrumentation. You can analyze a sample via a different method. You can use X-ray fluorescence and ICP-MS and AA to look at different metals. And we'll talk about all those different techniques, but that's a good way to do it. And you can also send your samples to different labs. Like in my research, I'm really interested in trace metals in soils, and so in order to be sure that the data is both accurate and precise, I often send more than one of the same sample to a lab, and I frequently will send the same sample to different labs and see how those numbers compare. So, random errors, on the other hand, are always present and can't be corrected. So we do stuff like weigh something a bunch of times so that we could try to quantify the random errors. But they result from stuff like electronic noise, weighing errors, having different people make measurements, or having the same person on different days making measurements. And, is this 2.4 or 2.5? I don't know. Those are the types of things that are random errors. You can't really correct for that. You can try to be as consistent as possible, but there's still errors. All measurements are still affected by random errors, no matter how careful. So the heart of this matter is that you can have precision, where your numbers are all very close together, so that would give you a small standard deviation. And they could be accurate, where you have the mean is very close to the true value. So each of these measurements, if you average it, it's very close to the center of the target. But clearly, none of the individual measurements are anywhere near the center of the target. So, but accuracy and precision are two different things. But what you ideally would like are both measurements that are both accurate and precise. So always hitting the center of the target. So precision, if you are precise but not accurate, that might indicate some systematic error. If you are accurate but not precise, then you would be looking at a random error, generally. Another thing to think about when you're thinking about errors is the absolute uncertainties associated with each of the techniques that you're using. So for example, an analytical balance has an inherent uncertainty of 0.3 milligrams. And that's true for not just the analytical balance, but for all the glassware as well. And so there's tables in Chapter 2 that talk about the different uncertainties associated with different volumes of these different glassware. So a 50 milliliter burette has a different absolute uncertainty than a 25 milliliter burette, and the same for all the glassware. So that's something to think about as well. All right.